Alright, in this video lesson we will be learning about simple machines, what they are, what they're used for, how to make some calculations about what we expect the machine's performance to be. So what we need to know is what a simple machine is. And so a simple machine is something that's used to change the amount of force or the direction of force on an object. So oftentimes machines are designed so that the user can apply a smaller force over a large distance so that you can move something that's like too heavy for you to pick up or otherwise too hard to move. Okay, that's oftentimes but not always what simple machines are used for. Sometimes they can be used to increase like the speed that you're going at, for example like in a rowboat, or just for convenience like the size they need to be. Sometimes it's a matter of just changing direction because it's easier to push than pull or easier to pull than push in a certain situation. One thing that a simple machine doesn't do is it doesn't reduce the amount of work, as we'll talk about. So some terms that we need to know when talking about simple machines are highlighted here. So we need to know about the effort force, which is what we put in. The resistance force is what you get out of the machine. And the mechanical advantage of the machine is then the ratio of those two. And we'll be using that idea of mechanical advantage a lot as we go through this. Okay, I have a simple machine song which I won't play right now. You can play it on your own if you want to. So there's 6 different types of simple machines, and a simple machine is like just has one part. And you probably have learned about these like in elementary school, but you didn't go into the math about them. So there's the lever, pulley, wheel and axle, incline plate, and wedge, screw. So we'll be going a little bit more in detail on each one of these. Okay. So we'll actually do this in class, so we'll go through and see if we can match up these different items so you can kind of try this on your own now, see if you can figure out what they are, and we'll talk about that in class tomorrow, like which one's which. Compound machines are machines that are made up of 2 or more things, so 2 or more simple machines. So as simple as a scissors looks, it's actually a compound machine, and again, we'll go through this activity tomorrow in class. So a lever. If you look at what a lever is, it's a rigid bar that's free to move around a fixed point called the fulcrum. So we need to make sure we understand what a fulcrum is, and I'm sure I have a picture of levers here. Okay, so again, the fulcrum is this pivot point in the middle here that the lever goes around. The side you push on is called the effort arm. That's where you put in the effort force. And the side where your load is raised up is called the resistance arm. And that's where the resistance force is applied to the lever. Okay, and so here's some different examples of levers. So actually like a tennis racket is a lever. It's kind of an extension of your arm, which is also a lever. So when you're using a tennis racket, like depending on how you're using, if you're doing a forward forehand or a backhand, the fulcrum is either going to be your elbow or shoulder. Okay, the effort arm is the distance at which your hand applies the force at, and then the resistance arm is further out on the racket. And here's one where actually it's the speed, because it increases the speed at which you hit the ball when you have it further out. Same thing for like a bat or a golf club. All right, we're not going to watch a video about lever. So the calculations involved with levers is if we want to know what the mechanical advantage of a lever should be, as in how much should the lever multiply our force by, the formula is given here that it's our size of our effort arm divided by the size of our resistance arm. So if I want to know what would the mechanical advantage of this lever be, I look at, okay, so I've got my effort arm and it's maybe, I don't know, guess 2 to 3 times bigger than my resistance arm. And so I guess I actually measure out as 2. So this lever would have a mechanical advantage of 2 because that effort distance is twice the resistance distance. That means, for example, if I was trying to lift something that was 100 pounds with this lever, I would only have to push down with 50 pounds there, okay? Because the lever is multiplying my force by 2, okay? So we're going to work through some example problems here. So this is just some notes, but let's look at how we actually work out an example. So we have 2 different formulas that I've introduced so far that tells you how big your mechanical advantage is. So it can be your effort arm as it relates to your resistance arm, And we also see the mechanical advantage can be relating your force out to your force in. So in this example problem, I want to know how much force will I need to put in to lift this very heavy thing. Okay, so first I have to find what is my mechanical advantage. So I look at the lever and I say, okay, my effort arm length is 5 meters. My resistance arm length is 0.5 meters. And so that tells me that my mechanical advantage must be 10. So now I know over here that my mechanical advantage is 10. And 100 pounds is what I'm trying to get out. So I look at, well, how much force do I have to put in to do that? Okay. And 10 pounds is what I'll need to do. So this is the type of problem we're going to be solving with levers, is looking at how much force do we need to put in to get out what we need. Okay. So now levers are not the only thing we could be using. Could be using pulleys. Okay. So pulley is just a grooved wheel that has a rope going through it. And with pulleys, we can have there's some examples of pulleys. The way we change the mechanical advantage of pulleys is looking at how many pulleys we're using. So the more pulleys we use and the more strings we have looped around it, the more mechanical advantage we have. So for this pulley system here, we can see that we're only pulling on one rope, but the load down here is supported by 1, 2, 3, 4 ropes. And so this, because if I was pulling with, say, 10 pounds of force here, there's 10 pounds of tension on this rope. So that means there's 10 pounds here, there's 10 pounds here, there's 10 pounds here, there's 10 pounds here. I'd be able to total lift up 40 pounds. Okay, so each supporting string gives you, multiplies your force. So here the mechanical advantage would be 4. Okay. We'll try out this problem in class. Again, I don't want to make this video too long. We'll do some stuff in class. We're just kind of trying to get you someone introduced here. So a wheel and axle is made up of 2 circular objects. Okay, it doesn't have to be like a wheel on a car, so we can think about even like a screwdriver is actually a wheel and axle. Okay, so basically a doorknob, okay, steering wheel, all wheel and axles. And with a wheel and axle, usually what you do is you put your force on the wheel. Whoop. Okay, so you turn the wheel and that causes the axle to turn. So the mechanical advantage is usually the wheel radius divided by the axle radius. All right, so make sure you're getting all these different formulas down for the different pieces. An inclined plane is just a sloped surface, and so inclined planes are used to raise things up to different levels. So like a ramp for getting a wheelchair into a vehicle, or basically anything that we think of as a ramp. So for an inclined plane, since we are raising an object up a certain height, that is what is important. So the mechanical advantage is going to be, how does the ramp length, the length that we have to push the object over, how does that relate to the ramp height? Okay, how high it's actually being lifted. All right, and again, we can work some together in class. They're all basically the same as that lever problem. So again, in the interest of time and not making you have to sit and watch me work these out at home, we'll just go through this real quick. So a wedge is kind of like an inclined plane, but instead of lifting things up, a wedge is used to pry things apart. Okay, so the way a wedge works is I push down on the wedge, and when I push down on the wedge, it causes whatever I'm driving it into to separate or be pushed apart. Okay, and so I put my work in down the length of the wedge, and the wedge does its work across the thickness of the wedge. So that tells us how those two are related. A screw is basically then an inclined plane that's wrapped around a shaft. Okay, and we all know what a screw looks like. So we won't be working any problems with mechanical advantage of a screw because it's kind of tricky to measure it, but it does have one. Okay, and we'll also be talking about, there's a lot of things that are screws that are other than like wood and machine screws. So like a fan is a screw. Okay, or like a propeller on a plane is a screw. Anything that basically turns a circular motion into a linear motion. That's what a screw really does. Okay, so like a spiral staircase in a way is a screw. Okay, and here's just some other equations that I forgot to put in and type up nicely, but that we'll need. Okay, so that again, we already know work equals force times distance. For a perfect machine, then the force times the distance I put into the machine equals the force times the distance I get out of the machine. So again, that's for a perfect machine. Basically, for a perfect machine, I'm just saying the work I put in equals the work I get out. The efficiency of a machine is then related to how much of the work I put in do I get out. And at most, efficiency can be 100%. You can never get more work out of a machine than you put in. You can never get more energy out of anything than what you put in. So simple machines, we're going to quantify that. Okay, so we're going to look at, like in lab, we'll be measuring how efficient our machines are to see how good of a job are they doing taking the work I'm putting into them and getting work back out of it. Okay, so I believe that's all I have for right now. Okay, and again, we'll work some problems in class. Let's see if I can stop this video so you don't watch me like bum. Where did my thing go? Uh-oh. Somehow I've got to stop this. This is probably really entertaining for you. Player. Huh. Well, this is just awesome.